All right, let's get into it. Today, we are going to break down the most fundamental rules of the entire universe. I'm talking about the tiny, tiny building blocks that make up, well, everything. You, me, the screen, the air we're breathing. We're diving deep into atomic structure and how atoms connect with each other. But first, let me ask you a question. What are you actually made of? I mean, really. If you could zoom in on your own hand, way past the skin, past the cells, down to the very, very smallest level, what would you find? The answer is kind of mind-blowing. So here's our game plan. We're going to start with the very first idea of what an atom was. Then we'll cover how scientists basically cracked it open. After that, we'll look at the modern blueprint for an atom, figure out what its number one motivation is, and then, finally, see how that motivation makes atoms hold hands or bond to create literally everything you see around you. Okay, so our story starts with a really, really old idea. Think ancient Greece. But it didn't really get scientific until the early 1800s. The basic concept was simple. Everything is made of these tiny little particles that you just can't divide any further. A guy named John Dalton came along and proposed that atoms were these tiny, solid, indestructible balls, the absolute smallest thing you could get. And, for the time, it was a brilliant idea. Of course, we know now that he wasn't quite right. We know atoms can be divided into even smaller pieces, and we also know that not all atoms of the same element are identical. Some are a little heavier, what we call isotopes. But hey, Dalton's theory was the first big step, and you gotta start somewhere, right? So, how did we get from that simple, indivisible ball to what we know today? Well, it's this awesome scientific detective story. Seriously, you had these brilliant scientists, each one finding a new clue, piece by piece over a few decades. It all kicked off in 1897. J.J. Thomson found the electron, and that was the first clue that, wait a minute, maybe there are smaller things inside an atom. Soon after, Goldstein found the proton, its positive counterpart. Then came this huge aha moment in 1911. Ernest Rutherford discovered the nucleus, this tiny, dense core, and realized the atom is mostly empty space. And the final piece of this puzzle clicked into place in 1932 when James Chadwick found the neutron, the neutral particle hiding in the nucleus. The team was assembled. So let's properly meet these characters. First up, the electron. This little guy is tiny, has a negative charge, and it's always zipping around outside the center of the atom. It is so incredibly light that when we're counting up an atom's mass, we basically just ignore it. Its mass is negligible. Now, in the center, in the nucleus, we find the proton. It's got a positive charge, the exact opposite of the electron. But here's the kicker. A single proton is almost 2,000 times heavier than an electron. So this is where all the real weight, the real substance of the atom is. And finally, rounding out our trio is the neutron. The name pretty much gives it away. It's neutral, no charge, positive or negative. It also hangs out in the nucleus right alongside the protons, and it weighs almost exactly the same as a proton. And that's it. These three particles, they're the ingredients for every single atom in the entire universe. Okay, so now we know the parts. Let's look at the blueprint. How do these three particles come together, and more importantly, how do we read the specs to know what kind of atom we're looking at? This little table sums it all up perfectly. To keep things simple, we give them these relative values. Protons have a charge of +1, electrons -1, neutrons 0. Easy. And for mass, protons and neutrons each get a value of 1, and the electron is basically 0. See? Nice and simple. Now here is the single most important thing to remember. What makes an atom, well, what it is, it's the atomic number. This is just a fancy way of saying the number of protons. That's it. If an atom has 6 protons, it is always carbon. If it has 8, it's always oxygen. The number of protons is like the atom's fingerprint or its social security number. It defines its identity. The other key spec is the mass number. Now remember how the electrons are basically weightless? That means all the atom's mass is packed into that nucleus. So the mass number is just the number of protons plus the number of neutrons. That's the total weight. And because we have those two numbers, we've got a super simple trick to figure out how many neutrons are in an atom. You just take the total weight, that's the mass number, and you subtract the number of protons, the atomic number. Whatever's left over, that's your neutron count. Simple subtraction. So we've got the what. We know what an atom is made of. But now for the much more interesting question, why? Why do atoms do things? Why do they bother reacting and bonding and making stuff? It all comes down to one single, incredibly powerful motivation. It's called the octet rule. And here it is. Atoms are happiest, or as a chemist would say, most stable, when their outermost shell of electrons is full. And for most atoms, full means having 8 electrons. This is the driving force in all of chemistry. Atoms will do just about anything, gain, lose, or share electrons to get to that perfect, stable number 8. And how do we know this is true? We just have to look at the cool kids on the periodic table, the noble gases. You've got helium, neon, argon. These guys are famous for being loners. They're super unreactive. They don't like to bond with anything. Why? Because they don't have to. They were born with a perfect, full outer shell of electrons already. They've already achieved chemical enlightenment. They're the goal everyone else is striving for. So if the noble gases are living the dream, how do all the other atoms get there? Well, they can't do it alone. They have to interact with each other. They have to form connections, what we call chemical bonds. This is how they reach that stable state. Now, there are 2 main ways they do this. The first is called ionic bonding. This is basically a transfer. One atom completely gives an electron to another. The second way is covalent bonding, which is all about cooperation. The atoms decide to share electrons instead. So think of it this way: give or share. Let's look at a classic example of giving. Okay, meet sodium. Sodium has a problem. It has one single, lonely electron in its outermost shell. This is super unstable. To be happy, it desperately needs to get rid of that one electron. If it can just lose that one, the shell underneath is already full and stable. Now let's meet chlorine. Chlorine has the opposite problem. It's got 7 electrons in its outer shell. It is so close to having a stable 8. It just needs to find one more electron from somewhere, anywhere. So you can see where this is going, right? Sodium, who needs to lose 1 electron, meets chlorine, who needs to gain 1. It's a match made in chemistry heaven. Sodium is more than happy to give its extra electron to chlorine. And just like that, bam, both atoms get what they want. They both now have a stable, full outer shell of 8 electrons. But wait, there's one more step. When sodium lost a negative electron, it became positively charged. And when chlorine gained that electron, it became negatively charged. And what do opposites do? They attract. This powerful magnetic-like attraction between the new positive sodium ion and the negative chlorine ion, that is the ionic bond. And that's what holds them together to form sodium chloride, which you probably know as regular old table salt. And that brings us to a final big picture thought. Everything we've talked about, these protons, neutrons, electrons, all following this one simple drive for stability, it governs everything. So, if all matter, from a boring old rock to a giant star, to you and me, is just a different arrangement of the same few particles following the same simple rules, then what is it that makes life in all its incredible complexities so special? Something to think about.